saka rikatenderera mberi nepresentation yedu. Saka tanchiti chatter's principle. So these are the things we are going to cover. So let's proceed. That's the principle stated for you. Tatunofana kuziva kuti isusu kati equilibrium shifts to the left, kureva ku left hand side kwako, which is kuside kunowanika ma-reactants. Ukati it shifts to the right, urikutaura kuti iri kuenda kuma-products. Saka it's important to be able to use this term. When you say left, you're saying backward. When you say right, you're saying it goes forward. So there are conditions that are going to promote the forward reactions, and that other conditions are going to promote your backward reaction. Okay, takaona effect of temperature, and the effect of temperature depends on the nature of the reaction to begin with. Is it an endothermic reaction? Is it an exothermic reaction? So if it's an exothermic reaction, if it's an endothermic reaction, there are going to be differences. So example here takabengari endothermic reaction. Yatiri kurefer chiti endothermic reaction ndo forward reaction yacho. Chauti backward inenge iri exothermic. So basically in a reversible reaction we have both an endothermic and an exothermic reaction. Saka inonyorwa pasign apo after the equation inenge iri forward reaction yacho. Tichiti forward reaction yedu in this case is endothermic, so the backward is exothermic. In other words, the forward reaction requires heat energy in order to take place, whilst the backward reaction produces heat energy. So the change in temperature now is going to depend on the effect on equilibrium is going to depend on whether the reaction is going to be endothermic or exothermic. Saka takati increase in temperature. Saka uka increase the temperature, remember Chatter's principle iroda kungoposa zvawaita. So uka increase the temperature iyo ida kudzikisa. Saka todzikisa say temperature by taking the heat. How do we take the heat away from the system? We use our endothermic reaction. So the endothermic reaction will take away the heat because it requires heat. So an increase in temperature will promote the endothermic reaction. A decrease in temperature will promote the exothermic reaction. So yeah, this is just a recap. Okay, let's move on and see what else affects a system in equilibrium. So kuna pressure. So pressure is from gaseous reactions. So for example, you're in a sulfur dioxide plus oxygen to give us sulfur dioxide, you can see that all of those things that are participating in that reaction are gases. So katamba pressure papa is going to have an effect on the equilibrium, whether it's going to be forward biased or backward biased. It's going to be shifted towards your right or towards your left. Saka ngata ise isusu ukawedzera pressure chichinoitika. So we go back to that principle that we learned in O level. You count the number of moles that are on your left and the number of moles that are on your right. Tikatasa ko left kwedu kune sulfur dioxide 2 moles. Kova kwaita oxygen 1 mole. Saka kune total of how many moles? 3 moles. Total sako right kune 2 moles. Saka it's 3 versus 2. Yes, ukawedzera pressure iwewe. Tatile chatila yada kuita sei? Ada kudzikisa pressure. Saka kuti pressure idzikire tinopromota reaction inofoma ma fewer moles. Some fewer moles are kuwanika ku right. Saka an increase in pressure will promote the forward reaction or the formation of a fewer moles, because fewer moles are going to mean a low pressure. They are going to lessen our pressure. So if you increase pressure, Chatter's will decrease pressure by promoting the reaction that produces fewer moles. So you promote the forward reaction. So in other words, our equilibrium shifts to the right when you increase pressure. The reason why takati pressure / concentration is that the same effect will happen to systems that are in aqueous systems. Is zvatirikutaura for pressure tinenge takungoreplace weight pressure na concentration kana dissolved in water. So pressure and concentration are explained in the same way. They have the same effect, only that pressure is for gaseous systems, whilst concentration is for aqueous systems or aqueous reactions, to be simple. Right, so tangent is also when you increase pressure, the pressure shifts to the what? To the right, where there are fewer moles. So more sulfur dioxide reacts with oxygen to form sulfur trioxide. Okay, so let's move on. What happens when you decrease pressure? According to Le Chatelier's principle, if you decrease pressure, the system would want to increase pressure so as to minimize the effect of what you would have done, right? So the position now shifts to the left. You have decreased the pressure, it wants to increase pressure. How does it increase pressure? It promotes the reaction that is going to produce for you more moles. So when you have more moles to your left, where there are 3, there's going to be high pressure. Remember, the pressure is coming from these the individual molecules bouncing off the walls of the container. So when you have more moles, you have more particles, more molecules, so pressure will increase. So how do we do that? Let's just make more moles by going to the left hand side of our equation. So it will shift to the left, and sulfur trioxide is going to break. So more sulfur dioxide and oxygen molecules are formed by the decomposition of sulfur trioxide molecules. So this is what would happen with the pressure. So you can explore concentration. Any equation here, AQ, which is happening in an aqueous solution, it's concentration. So let's just use this as an example. If it were sulfur dioxide AQ, oxygen AQ, and sulfur trioxide AQ, then you would say concentration. What happens if I increase concentration? It would move towards the right. What happens if I decrease concentration? If I decrease concentration of either sulfur dioxide or oxygen, then the equation will move to the left to try and increase the concentration of sulfur dioxide or oxygen. So I can alter the concentration of either sulfur dioxide, oxygen, or sulfur trioxide, and the system will try to increase or decrease the concentration depending on what you would have done. So I'll give a specific example that involves concentration, but you can explore that relationship. Okay, so let's move on to something else. So basically that's Le Chatelier's principle. Let's learn this, which is easy to understand. Bronsted-Lowry theory of acids and bases. What does it mean? It simply means an acid is a proton donor. Anything that donates protons, which are H+ ions, is an acid. So that's an example. Hydrochloric acid plus water. What happens? Hydrochloric acid is going to donate a proton to form H3O plus AQ and your Cl minus. So we say the HCl is an acid because it has donated a proton. Likewise, a base is going to be a proton acceptor. So a proton acceptor will accept a proton. For example, ammonia can accept a proton from water to form the ammonium ion and OH minus ion. So that's basically the provisions of this theory, that anything that donates a proton is an acid, anything that accepts a proton is a base. So we're going to come across this a lot. Okay, so let's move on to something else. So apa ndo pane imwe nyaya apa yakakosha, acid base dissociation constant. So in this video I may not exhaust this, but let's start. Sakana tauri nyema acids nema bases, kune ma strong acids nema strong bases, andika. So ma strong acids nema strong bases, they fully dissociate to give protons. For example, we just said acids donate protons, right? So an acid will to dissociate, for example, in HCl, it will break, not dissociate. A large number of molecules are going to break. In fact, let's just say all the molecules. Sakaiwoka na wanga une 2 moles per cubic decimeter of your acid. All the 2 moles of the acid that are present are going to break into H+ and Cl-. That is what it means when we say fully dissociate. If we say partially dissociate, we mean out of the 2 moles, maybe only 20% of the total number of moles or HCl particles that are there are going to dissociate or fully dissociate. The rest remain intact. So you need to know what we mean when we say fully dissociate, when we say partially dissociate. So what are we saying? We are saying strong acids. Once you say strong, whether you're going to say acid or base, you just need to know that it will fully dissociate. So for acids, they will fully dissociate to give protons. And then when we say a weak acid or base, it will partially dissociate. In other words, a large fraction of the molecules of the acid or base are going to remain as they are, right? And a few are going to, of course, dissociate, right? So let's move on. You need to be aware of these terms, right? So those are examples of strong acids, strong acid, hydrochloric acid, weak acid. So you can see that my pH range is there. Sodium hydroxide is a strong base, ammonia is a weak base. So you need to know that you classify acids and bases into either strong or weak. Saka nyaya dissociation constants ndo inozotibatsira kuita categorize kuti how strong is your base, how strong is your acid. Andika so specifically nyaya dissociation constants iri useful when you speak of weak acids or weak bases. Ikoko ndo kwainonyanya kutishandira because tinoda a scale yekuti how weak, because kuma weak acids ikoko togona kuwana imwe iri stronger, so we need something that tells us how strong is a weak acid or how strong is a weak base. Saka kune scale yatino create even kuma weak acids and weak bases. For strong acids and bases, we don't need a scale. We don't really need a scale. We need a scale especially for the weak acids and weak bases. So our acid dissociation constants are going to be very useful, especially when we talk about these weak acids and weak bases. And Edgar, all right. So let's see. This is an example for weak acid, ethanoic acid that dissociates to form an ethanoate ion and your hydroxonium ion as before. Okay, so let's explore this. So Ka means acid dissociation constant. What does it mean? What does it mean? What does it imply? Okay, so when you have an acid represented by Ha, it's going to dissociate to form your H plus ions and A minus ions. So A minus ions are called the conjugate base. The conjugate base. Why? Because you can see it's a reversible reaction there, and so that my A minus ions are unconsa to accept a proton also carry my HA, and so to conjugate a base. Acid yacho ndo HA, and so kana uda ku calculate acid dissociation constant, not is equal to the concentration of H plus ions times the concentration of A minus ions over the concentration of HA. When you divide that, you get a number which is going to represent your acid dissociation constant. So let's look at some examples. So for the example of ethanoic acid, the Ka expression, you must be able to write this Ka expression as well, where you don't now just put an H plus and A minus and then HA, you put specific ions for the specific acid. So for the ethanoic acid, we are going to have our ethanoate ion CH3CO minus times H plus times concentration of H plus times concentration of CH3COOH. Iso zvine marks to be able to write an expression for Ka for a specific acid. So the larger the Ka, the stronger the acid. In other words, when you have a large Ka, it simply means that our concentration of the conjugate base, for example, CH3CO minus there times H plus ion, that number that we get is larger than the number that's at the bottom, meaning that we have more products than we have of the reactants. Remember, the reactant is the actual acid, the intact acid. So if we have less of the intact acid and more of the products, that means this acid is willing to donate protons. So it's stronger the more we have products and less of the reactant or the acid the stronger the acid. So Ka so the larger the Ka value, it means we have more of protons in the conjugate base, meaning that our acid is willing to donate a proton. It's more willing, hence it's a stronger acid. So you can look at those values just for comparison. Right, so to make the videos short, let's end with Ka. So I'm going to give you an exercise and I want you to look at questions where you are asked to calculate Ka values and comment on Ka values. So let's meet in the next video.